streaming on. Okay, so this is it. So then let me see where I am here. Okay, so I just explained that we have, two extremes. One that is fully based on analytical equations, and that's going to be hard to follow because it requires so many parameters that are difficult to get. And then another extreme that is fully based on measurements. Doable, but needs a lot of measurements. And sometimes we don't have those measurements. So what we wanted to do is that we wanted to meet in the middle. So we wanted to use these analytical equations and we want to express them in a way that allows unknown parameters to be defined from manufacturer's catalog. That's in a nutshell. That's what we wanted to do. Okay, so this is an explanation. It seems that it's a little too small to fit in the screen. So basically, this is a little bit more explanation. So in order to model this spool position, you need to know quite a bit of info. You have to have quite a bit of information, including how much pressure is applying to components, how is a friction, how is a flow, a spring component, so on and so forth. So that's going to be the one that is needed if following the analytical approach. Now, here are the different approaches. So the empirical models, those are the fully based on measurements. And then the analytical models fully based on mathematics. And the one that is in the middle is called semi-empirical modeling approach. And that's pretty much what I explained. So we get started from analytical equation with reasonable amount of manipulation. We're able to express them in a way that unknown parameters can be excuse me. So the cake eventually wasn't a good idea. So it went to my throat. Okay. Hopefully it stays off on my throat. So parameters again can be get from manufacturer's catalog. Now here's an example. This tells you how it goes. And this is a throttle valve where there is no So it's still in my throat a bit. So I need to make more water. So here's an example, and this is, so be careful when I'm explaining this because this is what we're going to repeat over and over again. So the throttle valve where there is no moving component, it's just the drilling where the flow is traveling. So this drilling here is reducing the pressure from P1 to P2. And we are assuming that the pressure difference over this component is significant, so it's higher than that, say, 4 bars. So we are assuming that the flow, it is turbulent in a type. So we are not assuming this to be laminar in a type. And that's typically the case if you have just a short drilling like is the case in this picture. Now, analytical equation for that component can be written like this. So under the square root, you have the pressure difference. That's pretty much, that dominates the behavior. And then I have here dimension of the component. So I have here the D, which is the diameter of the drilling. Then I have here P, and then divided by 4. And then this is a discharge coefficient that is used to categorize this particular drilling. This is something that you can get again from pre-calculated tables, but tells you a little bit that this symbol component, symbols that you can find, already needs 2 parameters that are a bit challenging to get. And these 2 parameters that are a bit challenging to get is this discharge coefficient. Of course, you can use CFD to compare it or use a pre-calculated tables. And often simple component like a diameter, that too may be difficult to get because physically this could be middle of the pipes, and it may be hard to measure how much is this diameter. Of course, there is a setup that you can make it happen, but generally speaking, it's already a little bit of challenge. So what we're going to do then is that we're going to replace all these parameters by one parameter that is called semi-empirical parameter. We are losing no information whatsoever because the semi-empirical parameter is the one that is including everything that was defined in a previous original equation, this one here. Okay, so excuse me. So now that goes off. Okay, so again, this is original equation that includes the parameters that are a bit difficult to get. All these parameters will be replaced by one, which is called semi-empirical parameter, and that includes everything. And if you substitute this one here, you will get exactly the original equation. Why we do that? Why is that we do that? Well, we do that because manufacturers are providing characteristic curves. And from the characteristic curves, we can get automatically this semi-empirical parameter, and that's the only thing we need to know. All these discharge coefficient, diameters, and others are included there. So that's the trick behind. Here's an example. So I have here characteristic curve, and now this curve is such that this x-axis here is a flow rate, and the y-axis here is a pressure difference. The first super important observation when you look at that curve is the fact that this is actually quadratic curve. So it's not the linear relation, but quadratic relation, telling me that yes, I can model this particular component by using a turbulent flow type. Okay, then I need to use this characteristic curve to define how exactly is this throttle valve in question. How are the properties associated to this one particular valve? How can I make that happen? Well, I know that the quadratic curve is always a quadratic curve, so the only thing that I need to do is that I need to take the one value out of this curve, and now let me make it this bit bigger. So I'm taking the value from the 30 liters per minute, and I can see that that takes a place when the pressure difference is 100 bars. Using that information, I can substitute 30 liters here and converting that to be in SI units, because liters per minute is not the SI units. And then I can take my 100 bars, convert that to be in SI units as well. And once I do all this conversion, this is how my semi-empirical parameter look like. Now, look at the units. Units are a little bit painful here, so you can of course convert these units to be in millimeters and whatever you want.
Can you zoom in a little bit? It's smaller.
This one.
Maybe not that much.
Okay, so
Like
this one.
Yeah, right.
Okay, so the units is meter power 3 second square root Pascal, so it's painful. And of course, you can convert this to be any units you want, but roughly speaking, when you're modeling the hydraulics, it is, well, not roughly speaking, but it is highly recommended to use meters all the time, because once you started to convert these units, there is a high risk that you can introduce a mistake there. And once there is a mistake, then of course it's not going to be operating the way you think that it's supposed to operate. So again, the idea is that you take this characteristic curve, one point, doesn't matter which point because it's always following the quadratic curve, and then you just substitute the values from that to this semi-empirical parameter equation, and then you can compute how much is the semi-empirical parameter. And then you're good to go and express equation that defines how much flow is traveling through this particular component. Okay, so how it goes then? It goes such the way that you have here, first of all, the semi-empirical parameter, and then you're using something that is quite, well, it's must-have in a computer simulation. Then you have here sine component. This takes care of what's the direction of the flow. And I'm going to explain that to you in a second. And then you have a square root, and under the square root you have pressure difference. Now, if you look close at the pressure difference is within the apse. So this is always producing you a positive value. And I've always wanted to have a positive value because I don't want to deal with the cases where under the square root there's a negative value. I mean, mathematically I could maybe handle that, but I just don't want to do that in a computer simulation. So that's why I'm saying that it's always having the positive value. Now, if it is always having the positive value, it means that the flow is traveling always from here to P1 to P2. And you know that that's not necessarily the case because it is highly likely and it's possible that the pressure B is having the higher value than, P2 is having the higher value than the P1. And if that's the case, then the flow is traveling opposite direction. So I have to be a means to handle that too. That one will be handled by using the sign component. So the sign component is only producing you two values. It's either producing you 1 or -1, depending what's the function inside of the sign function telling you. So it goes such the way that if, the sign, how can I explain, the sign delta P is having the negative, this less than a 1, then it gives you -1. Then if this is having exactly the 1, this is going to give you 1. And then in this case, it's going to be 1. So it's only converting the direction, nothing else. And I'm doing that because I want to keep this component under the square root being such that it's always producing the positive value. So that's the way it goes. Okay, now let's move on to more interesting components. And the one that takes quite a bit of time today is a direction valve, directional valves. And we're going to look at a little bit about the basics. And then there's a one in-class quiz that is related to this directional valve. And then if we have a time, we're going to move on to cylinder and even the pump, which I don't think we can do it today, but we'll see. Okay, here's how the direction valve look like. Now I have the direction valve here that is connecting 4 different ports, and let me make this bigger to make it clear. So it's connecting pressure channel. It is connecting that to or A or B. These are the one that is going to component. And then the 4th channel that is connecting is a tank. It not necessarily need to be a pressure and the tank lines, but it's these 4 lines that it is connecting. And this kind of valve can have 2 operation conditions. Either the pressure line, which is here, it is connected to the port A, and then that means that the B is connected to tank line, or other way around. The pressure may be connected to this B line, and then A is in that case connected to tank. And it really depends how is that you're moving the shaft back and forth. And this is the one that again consists of moving spool, and the spool is operated by a shaft. And when you look at the spool, it works such the way that there are lands that are connecting flow to different directions. So these lands or drums are the ones that are kind of like the fundamentals of this operation. Clear? Okay, so then if I would have this kind of valve, let me make this a bit bigger. Direction valve, the one that is showing in this picture here, what would be the drawing symbol associated to this? And this is not the in-class quiz, but this is just to take your attention to me a bit. So is it going to be the one that has 2 operation conditions? Obviously it's connecting 4 ports, which are pressure, tank, A, and B. So it's going to be this option A, or is it going to be this option B, or option C? And now we're going to vote. So think about it, and I think that, first thing you need to understand is what are the operation conditions? Is there something that is in the middle, or is it something that is always connecting something to some other places? So my question is that, what do you think? Is it going to be this, let me change the color. What's the deal with this color thing today? So it's not, how is that I changed the color last week?
You have to click the little arrow that's pointing down, I think.
This one.
Yeah.
Now it stopped cooperate. Maybe I need not, I don't know. Okay, so let's use a red color. So I think I kind of like red. So it's okay. Okay. So what do you? How is your vote? Let me take this first off. Oh, God damn it. Okay. So my question again is that this is. Okay. So this is. Oh, look at that. So now it's coming. So this is how the component look like. Who is voting for drawing symbol A? You have to vote. Who is voting for A? You have to cast your vote. So is it so no one is voting for that? Okay, who is saying B? So what the rest? What is that the rest is saying? You guys are not voting. You have to play with me. So what is it you vote? You don't know. Okay, C. Okay, so the right answer is B. And B because, look, in here when the spool is in this connection, nothing is connected. So it's not connecting the pressure to A or it's not connecting the pressure to tank. It's just not doing any connection because land is completely closing all the connections. So I'm assuming that the land is exactly the size of these drillings. So nothing goes, that there is no flow whatsoever in this get area. All right? So that's how it goes. So this is important because the spool geometry itself defines quite a bit how are the features of the directional valves. And this in turn have to be or must be something that we are able to account in our simulation models. Okay, so this is the valve where we are assuming that there is a exactly same size of land that are the drillings, and then if that's the case, then it's fair to assume that in a middle position, and that's the middle position exactly how the spool is located in this picture. There is no flow in any direction whatsoever. If I'm pushing my spool to be positive X direction, that means then that the B will be connected to tank and the pressure will be connected to A. And if I gotta move my my spool to negative X direction, then the pressure will be connected to A, and then A will be connected to tank. Clear? Okay. So let's look at the one more thing here. So then the land can have very different geometries. So it's possible that the land itself is actually smaller than the drillings. And that's the case when in a middle position, all the channels are connected together. Or it may be the case, like we just looked at in a previous slide, or maybe there is a case that the lands are much bigger than the drillings. This is a little bit of special case because in this case, you have to move the spool. You have to move the spool a bit in order to introduce even a little bit of flow through this directional valve. Now, all comes important when we look in the relation about the opening and the flow rate. And this is the figure that shows the valve opening. And it's again the X direction, X here. And how is the flow? I'm not saying anything about the pressure difference, but how is the type of the flow through this component? This is opening, and this is, my spool when it is this having this symbol in a valve. This is the one that there is a, I need to take this off. This one here, when the lands are bigger than the drillings, means that I have to open the valve quite a bit, and still there is no flow whatsoever. And once I reach the point that the lands are losing the connection to drillings, then the flow takes place. and it's assumed that there is a linear connection between the valve opening and the flow rate. Here is assumed that the pressure difference remains the same all the time. So that's my assumption here. Then there's a proportional valves too, when the opening and the flow rate are not linearly related, but they are related, proportionally, like this one here. So that's called proportional valve, which is very good because it can introduce quite a bit of speed in a full opening, and then it's very accurate when you need to have an accuracy when you're approaching to your destination. Some of the cranes are using this technology because you can be fast and you can be accurate same time. And all that is possible because the valve opening and the flow rate is having this proportional ratio. Okay, but let's go back to the modeling business. So we are actually approaching the in-class quiz, and I'm kind of excited about the result that I got from the previous in-class quiz. So I'm actually again after this 100%. So I'm gonna hope that you can listen what I'm saying, because the next in-class quiz will be related to this, what I'm about to say to you. Most of the valves are operated by magnets, so they're electronically operated, so they don't have the stick like was the case in here. This is, if you can see this kind of valves, they may be using, maybe some of the trucks still have this kind of like the plate that is going down and helping you to unload the trucks. They may have this kind of mechanical sticks, but in a mobile application, when we're speaking about forest tractors or other modern mobile machines, they are typically operated by joysticks. So when you look at the cabin, they have a joystick, and the joystick actually is sending the signal to directional valves. And the directional valves are then in turn operated by, electronically, typically by magnets. And if you're pushing your joystick to one extreme, the directional valve will follow your signal. So how is that we can model the system like that? Well, we have to assume that there is a magnet that is big enough that it can follow your control signal. So if you're putting the valve fully open, then there's a magnet that can actually do that in reality, meaning that it's able to move the piston to one extreme. So how is that we can actually then do this modeling? Well, we can model the spool position in such the way that we having the first order differential equation, which is actually a delay equation, nothing else than a delay equation that follows the control signal with a certain delay. Because in reality, there's a delay. There's not possible that if you have a step that moves here to here, like no time, the position of the spool cannot follow that, but follows with a certain delay. And that delay is explained by this first order differential equation. So what I have here in this first order differential equation is a spool position, actually the signal that is coming from the joystick, and then the spool actual position, and then the time constant that defines how fast this particular component can react to changes in a control signal. Now, it means that if I have here time, and I have here, signal, and then also how the spool is following the signal. This signal could be jumped from, from 0 value to maximum opening. And the spool cannot jump from one location to another location, but it follows with a certain delay. So this first order differential equation will introduce this kind of delay. How long this will take, that one is defined by this time constant, tau. And that's the one we can get from manufacturer's catalog again. So the whole purpose of this equation, and this is what I'm going to ask in my in-class quiz, is I'm asking, hold on, going here. I'm asking, what is a physical interpretation of this equation? This equation. Do you know it? You don't know it. But let me explain it to you. So that's telling where is the spool position, because it's A delay equation that tells you how the spool is having its value with respect to control signal. So components again that I need in this equation is signal that is coming from the joystick, and then this is like a feedback value that telling how is the current situation of the spool, and then the third component is a time constant. So those are the three components that I need, and once I have those three components, then I can introduce this time delay equation, which is the first order differential equation. These two, by the way, have to be solved such the way that you can solve the u from this equation, and that's the one you can then use to define how much flow is traveling through your directional valve from one channel to another. Okay? Clear? Would you like me to repeat it? You say no, and what I'm going to do is I'm going to repeat it. So I'm saying that, physical interpretation of this equation is what? It is telling you the spool position of the valve. The spool position is needed in order to compute how much flow is traveling through your component. And, this one missing component, this one here, that is this time constant, that, like I mentioned earlier, that's something that you can get from manufacturer's catalog. Let's take a look at it in a second, like how exactly we can get it. But prior to that, just that you understand that I'm serious about my in-class quizzes, this is what is coming. Look at that. Physical interpretation of equation below. Pressure drop due to the valve, flow through the valve, spool position, number of ports in valve. Physical interpretation of that equation. Okay, so I'm going to put the in-class quiz on, and then I'm going to explain something else, and then I will be going back to that next. Physical interpretation of equation below. Pressure drop due to the valve, flow through the valve, spool position, number of ports in valve. No, you're not able to help your fellow students. So please don't help them. Okay, so, and while you're thinking that, let me look at this equation. So this is an equation that defines spool position. Now we need here this time constant telling how fast spool can react to signal changes. And this we can get from the manufacturer's catalog, because manufacturer's catalogs are providing something that is called border diagram. Border diagram tells you quite a bit about the quality of your directional valve. And, this is something that, you're looking at, like, you're actually sending the signal to your directional valve, which is a sine signal, and you're changing the frequency of that signal. That's what it is. And then you're monitoring how closely spool axle position can follow that signal. And it can follow it fine, particularly when the frequency is low. But when the frequency is getting higher, the spool is having, more and more difficulties to follow that signal. And eventually it's going to lose the signal such the way that the difference between the axle position and signal is becoming very large. And when the difference is going to be 45 degrees, we're going to look at an example in a second. Then it's considered that it's no longer accurate. And this is the value that you can take it from the manufacturer's catalog, put it here, and the time constant is here. Okay, so then the actual valve, the valve model can be described like this. So I have here flow through the valve. I have pressure difference. We can apply that to different kind of valves in a second. Then I have here the semi-empirical parameter that you can get from the manufacturer's catalog, and spool position. There is going to be more flow through the component if the opening is bigger, and less if the opening is smaller. And it is assumed to be linearly related. Of course, that depends on your case. So if there's proportional valve, then you cannot use this equation, but you need to use a different kind of equation. This is U. So this is real position. It's a little bit confused because it may be better to call it like X. Why is that I'm not using X? You don't know that. Me, no, I don't know that either, but I should use X because X would make you less confused. Because remember in the previous pictures, I was all the time saying X, and then suddenly what comes into play is U. You should file a complaint. No. But you know, this is what I realized, that this is not educationally very good. I need to change my explanation on my slides because X what we need. Yeah, we do need it. Because look at this. Where is it? Here. It says X. You know, this is X is measured to this direction, so of course I should use X, not U. I'm using actually two variables to define the same thing, and this is, you know, if you look at the scientific papers, you do something like that, it's almost like a criminal action. You are not allowed to do it. So, my apology. Okay, but we here. So this is how you define the flow rate to your component. And now, moment of truth. How is this? Okay, we have 10 students that are now thinking. Was it 96? 96 was the last time. So how is this time? I just got excited by myself. You know, I said that, 75, I said, not to make me disappointed. And then I realized, like, oh my God, I can make this 100% to happen. It's possible, it's doable. And now I'm after that 100%. So we have, this is the last in-class quiz today. And then in the coming weeks, there's only, let me think, just there may be 4 in total left. So his chances to get the 100% is getting thin. Okay, but now you guys all done? So is this it? Here's a promise for you. If it is 100%, I'm gonna close for today. Seriously. Seriously, that's what I'm gonna do. So here's my promise for you. Okay? Would you like to start packing your backpack? Oh, it was. Look at this. Oh, I'm so relieved because it was a pot of joke. Maybe it was me. You don't know that. Look at what I have here. Oh, that was a really, really close case. Okay, but the good news is this. We don't need to leave. So we can still stay here. So, nice. So, the correct answer is spool position. Spool position, which is, the next year I need to change this to be X to be a bit, more understandable. So this is X dot, this is X. And then here, this is supposed to be X, of course, to make it more consistent. Consistent is here what we need. Okay, but now let's close the case here. So here is how are the flow rates in different scenarios when the spool is having the positive direction, a positive value, negative value, and when it is in the middle. So in the middle, we are assuming that there is no leakage whatsoever, which is not actually according to reality, because in a valve like that, there's a little bit of leakage all the time if the land is exactly the size of the drillings. So it's not necessarily really the case. But now, something that I feel that is quite interesting is that, there's an idea to replace this type of the directional valves with digital valves. And I would like you to learn what is a digital valves if you're not aware of that prior to this lecture. But the idea is very simple. In this conventional valve, we have the spool that is moving back and forth. Now, instead of having spool that is moving back and forth, we could use a number of poppet valves. Certain number of poppet valves that is having 2 positions, open or closed. Open or closed. Then once we have these open and closed valves, and once we have a number of them, we can actually imitate the motion of the spool, and we can actually have a separate opening for A and B. And this is something that is quite interesting because, in a conventional valve, because it's all about the motion of spool, A and B are not separated, but they are following each other. So it's not possible to connect the cylinder piston rod side directly to tank without any pressure losses. You just cannot do it that because it's all about the spool position. But in a digital valves, you can do whatever you want, including the connection to tank with no pressure losses. And that's in short, that's the idea about the digital hydraulics. And next, what I would like you to do is that I would like to play a short video which is about the digital hydraulics. Now, this goes sets that I'm using a bit old-fashioned ways. I'm making the mic too close to my computer because this guy is not willing to cooperate.
In digital hydraulics, the system variables, pressure and flow, are controlled with multiple on-off directional seat valves. Each valve is solenoid operated and has only two possible positions, on and off. This is why the term digital is used. These valves are used to implement all valve functions, such as pressure, flow, and directional control. Contrary to a traditional hydraulic system, which has many different types of valves, a digital hydraulic system has a large number of only on-off valves. By connecting in parallel 3 on-off valves of different sizes, such as 1, 2, and 4, 7 different flow quantities can be achieved. 5 on-off valves can achieve the control resolution of a traditional proportional valve. A group of on-off valves in parallel make up a digital flow control unit, called DFCU. At least 4 of these units are needed to substitute a proportional valve in a hydraulic circuit. Each DFCU is used to control one of the 4 control edges. The main benefit of digital hydraulics is the ability to control each control edge independently. This reduces power loss and enables precise control. Additionally, seat valves have 0 leakage, as opposed to the high leakage of proportional valves. However, the challenge with digital hydraulics is the complexity of the control algorithm. Each valve needs to be controlled individually, and this results in large numbers of valve position combinations, although each valve has only 2 possible positions.
No. Okay, so he's not playing that. Good. We'll be with you in a second. So your question is, my mic is still not on, is it? So it's on. Okay, so your question is that why it is
Not used.
Oh, okay, so why not used? Well, it is actually being used more and more all the time. There are some difficulties associated to that because, like it says, digital, so it means that it's on and off. And if you don't have a lot of these digital valves, it can make your moment to be choppy. Because once you open the one unit, it can introduce significant changes in a direction. So it can lead to consequences that the cylinder is not moving steadily, but it's moving a little bit like, with the steps. So that's one challenge, but it's still doable. There's ways to get over that. This is quite a new idea, and I think that it still needs quite a bit of time to people to get used to this, and I think it is a major reason why it is not that heavily used. So when I was in a graduate school, I got a friend that was specialized in the hydraulics, and he's the one that is now doing the research related to digital hydraulics. And not long ago, I discussed with him and asked, what are the recent developments in digital hydraulics? And he said that now there is a major attempt to use a digital hydraulics, all the components that in your hydraulic circuit, including pump. And that I think that is quite significant because right now what happens is that we need to go all the way back to the first slide, the second slide. So here. So when you, oh, this is big mess, but let me take this, all this off. You know, in this kind of conventional hydraulic circuit, you have this motor that is running the pump. So here is this unit, and this is producing energy to your system. And the only control scheme you have is losing the energy. So it's losing the energy, though this makes no sense if you think about this as a whole, because you keep on producing energy and then you're controlling that by losing it. So what sense that makes in a modern world where we are really worried about energy efficiency? Now the new idea is that, you know, we are producing the energy for the system based on the need of the system. And that you can make happen with help of digital hydraulics. So there's a really clever and very fast system that realizes when the energy is needed, and then it gives the command to pump, and the pump is then either producing the power to system or not producing power to system. And that's a digital hydraulics that goes all the way to digital pumps. And that I feel that can introduce quite significant energy savings. So that in short. But what was your question? No, it was something else.
You answered it already.
Did I?
Yeah.
So you're happy?
Yeah, and last is also I thought.
Okay, so any other questions? Okay, now you're too scared to ask a question because then it's going to be a lengthy explanation about something not related to your question. No. But others, you're fine?
Yeah.
Okay, so then just before we close for today, let me just show you one example. So let me go back here. So this is one example how the parameters that are needed in a direction valve, how they can be defined. And then I have pictures that I directly took it from the manufacturer's catalog. Now the first thing that is mentioned in the manufacturer's catalog is that they mentioned that there's a nominal flow, which is a flow during the full opening of the valve is 24 liters per minute, and the pressure difference in that case is 35 bars. Now when I look at the manufacturer's catalog, there's a picture that shows me what's the relation between the valve opening, so the X is valve opening, and the flow rate. You can see that this relation is more or less linear. So I can use the equation that I introduced you previously. This is not proportional valve, and this is not the valve with the lands that are bigger than a drilling. So this is simple valve that I can use the equation used before. Now with help of this information, 25 liters per minute, 35 bars and a fully opening, I can compute my semi-empirical parameter. So 25 bars goes here, liters per minute, 35 bars goes here, and the opening is considered as a 10 voltage. This was defined in earlier places of the manufacturer's catalog. So that's my semi-empirical parameter. Then the time constant that I need, this is a border diagram, and this tells you how the valve is able to follow the signal, that is this kind of sine signal, where the frequencies keep on increasing all the time. So the frequency is actually here in x-axis, and you can see that the valve is able to follow the input signal with no problem until it reaches, let me see, 20 hertz. Then it's to be a little bit of difference. Now, depending if you wanted to have a full opening or the opening of 5%, there is a little bit of difference. Maybe we can look at the full opening. And if there is a 45 angle difference, that's roughly somewhere here. That's where it's no longer able to follow it. And that can give you the value that is, I guess that is somewhere here actually. Somewhere here, that's a 45 by the way. That's when it's not able to follow the input signal. So that's the value that you can take it here, put it here, and this is your time constant, and that's all you need in order to create your model. So with that, let's close for today. Then next week, which will be on Tuesday, we're gonna close hydraulics, and we're gonna discuss about the control scheme, and then one more lecture left after that. All right, so take it easy and see you on Tuesday. Is it Tuesday? Tuesday. Okay.